So right here, what I have is a divide by 8 circuit that I built in Minecraft. So basically, what's happening is this is counting from 0 to 7 over and over and over. So it's at 1, that's 2, 3, 4, 5, 6, and then 7, and now it's going to repeat. And the way we accomplish this is with D flip-flops, and we have to wire them into each other, and it continues the count to each bit. Hence these are labeled least significant bit and most significant bit, because this carries the most value, and this carries the least value. Now, if we go over here to see how it works, we have our clock, and this goes right into the first D flip-flop. All this does is pulse shortener, and it makes sure this doesn't stay on for too long, because otherwise it messes with the circuit. So the clock input, which is shortened to make sure it doesn't stay on too long, goes into these first two NAND gates. Basically what a NAND gate is it's an AND gate, but it's inverted. So not and NAND. So instead of both inputs having to be on in order for the output to be on, both inputs have to be on for the input to be off. And with that, you can pretty much only use NANDs for the entire circuit, which is why each D flip-flop is composed of 4 NAND gates and 1 inverter, which you have right here for this input over here. And they also each have a pulse shortener, just to make sure the length of the clock input is not too long. So, what happens after the clock, and this goes into each NAND gate, you also end up having the output of one of the last NAND gates have to go all the way back, as you can see, carry it back, all the way into this NAND gate, take the inverse of that, and put it into the NAND gate that's right next to it. So all these NAND gates are tied to each other in some way, and basically that makes a kind of a count. It'll go back and forth. Because what these inputs are, this is Q, this is not Q. So basically all that means is when this is 1, this is going to be the opposite of that. So it's going to be 0. This is 1, that's 0, now it's 0, that's 1. And what this allows you to do, well, Q, which is the actual input, this is what you're going to use for your count. The inverse of that is going to be the next clock input for the next flip-flop. As you can see, we don't have another one of these built over here. We just have this output going into it. And it also goes back into some other gates. And so, what that does, when you put this into another flip-flop, it's going to do the count again, but slower, and hence why these tend to stay on and off longer. So you see this one, it's turning on and off, but this one's staying on. And when this one stays on, this one stays off and on the longest. And what this does is it creates that count, because each successive one counts slower and slower. So, basically, that's how you create that count, is through these flip-flops. I'll try and pull up a schematic. You can see with these last 2 NAND gates what I was talking about, with how their outputs become the inputs of the other NAND gate. And what's not shown on here that is used in our circuit is that the output of not Q goes back into D, and that makes it count. Who knows, maybe I'll do something like this in the future. I think that being able to bring digital electronics into Minecraft with Redstone, with pretty few like translation errors. Only thing I had to change here is these pulse shorteners, and the rest of it is pretty much, you know, if you had to wire this, obviously they wouldn't be there wouldn't be redstone, but you'd have an IC, and you'd have all the gates in there, and you'd wire them pretty much like this, unless you had an actual flip-flop IC, which I think's neat. I think it's actually really cool, but yeah, I hope you enjoyed, hope you learned something, you kind of know how to count in binary now. Yeah.